I'd like to give another example on sampling, and particularly in sampling sinusoids. So I want to start by just talking about a sinusoid here where my frequency is going to be 1 kilohertz. My input is going to be 4 cosine 2 pi ft. And so if I sample this, remember what I'm taking is my time is now going from n times some sampling time, which is really n over the frequency. So simply plugging that into this structure and effectively kind of using that, I find that I get 4 2 pi f over f of s of n, which then tells me that my sampling omega, as opposed to my continuous omega, is now going to be 2 pi of f over the sampling frequency. So then you say, well, what do I get for that? Well, imagine if I sample this at 4 kilohertz, 2 kilohertz, 1.113 kilohertz, and then also at 1 kilohertz, what do I see? Well, that would then give me pi over 2 pi minus pi over 2, and then gives me something that's 1. So the pi over 2 is just straight plugging into it. In fact, this is the kind of waveform I get. Notice how granular it is. It's only sort of 4 points per period. There's not a whole lot in there. If I actually go right to the Nyquist, which is then 2 kilohertz, that's going to basically give me 2 points on each side. That's not very much. In fact, you can tell why it's the minimum to go anywhere I would be expecting there. If I sample below Nyquist at 1.33, that gives me an omega hat that's 3 pi over 2, which really means I've reflected this back, and so now it's minus pi over 2 in this case. So it's going to look a lot like this one, but it's going to be flipped. It's going to look like I'm going to have that, but it's going to be kind of flipped around. And it's kind of a little bit different in terms of the actual frequency I'm now referring to, because in some sense now it's saying that's the sampling, that's the number. I've effectively decreased where my frequency is. Even more interesting is what happens at 1 kilohertz, because it means that now it's 2 pi. And cosine of 2 pi n is going to be 1, no matter what n is. And so that's just 4, and that's a constant, and that's not what we started with. So you can immediately see that aliased me down to 0 frequency, which is kind of interesting to see these various pieces. So that's interesting, but now if I look about, let's imagine I have a sum of 2 of them. 3 cosine of a primary frequency, and then 1 times its third harmonic. And what I'm going to see is I get 2 frequencies that are in there, one 2 pi, one 6 pi. I can take a look at this at different sampling rates. So imagine now I'm doing this at 18 kilohertz. Well, omega 1 looks like I've got a lot of room to work with. And omega 3 is pi over 3, and I get this very interesting waveform here. If I go down to 6 kilohertz, I'm actually at Nyquist for the second term. The first term's got plenty of room. And you can kind of see what's happening here, but you can kind of see this structure. Looks very much like this one, but just subsampled down. That may or may not be good for what you're trying to do. And then, of course, if I go to 3 kilohertz, well, I completely lose the second one. Again, now it turns out to be a constant, and I get 2/3 over pi. It is important to kind of see all of the pieces of sampling, including what you get out of a Nyquist system. Typically, you'll want more than that just because this gets a little bit choppy. But again, there are things you can do with all of these systems and reconstruct and work with it in terms of afterwards. But it's just important to get a good visual picture of all of the moving pieces around sampling.